Welcome to part two of vector projection. Alright, so as we worked in the previous video, we derived this. Vector v projected onto A is equal to that using this idea and some fancy algebraic manipulation. Okay, now we're going to be using that right now. Okay, so before we use that, before, this is a previous idea. We broke down the vector v in the past in terms of vector I and j, and they are unit vectors in the direction of x and y axis respectively. The question is, can we break it down into not in terms of I and j, but some arbitrary vectors a and b that does not necessarily have any relation to x or y axes? And the answer is yes. Okay, so we're going to assume for the purposes of our class that the a and b are orthogonal, which means the dot product is equal to 0. Okay, so when you project the v onto a or b, you're going to have a sunshine over here and a little shadow, and that portion it will be v onto a, and you're going to have projection this way, and that will be defined as vector v projected onto b. And so this vector is same as this right here, right? Okay, so it goes this way, vector a onto b, v onto a, v onto b, this way. So we have this particular relationship, and we're going to resolve this, right? So that's the expression. So the way we're going to do this is we're going to resolve the vector v into components parallel to vector a and b, and we've defined what they are. And using this relationship that we just derived and applying the formula, we get this relationship. So the rest is just plug and chug, all right? But just keep in mind that this vector is being projected onto vector A and B, and there are some arbitrary, it doesn't matter what they are, arbitrary vectors. So what we have to do is a lot of calculation. So this represents a scalar multiplication of vector A, and this represents the scalar multiplication to vector B. So we're going to either increase or decrease the length of it, or we may even have a negative value, which means that we're going in the opposite direction. So the numerator of the first scalar is a dot v, which gives you, after the dot product, negative 22, and a dot a will give you 40. And we could go on to b dot v, and that will give you 13, and b dot b will give you a total of 10. Having said that, we need to sort of simplify this. So this implies that this is what? Negative 22 over 40, and that's going to give us negative 11 over 20, right? So the vector here, the scalar multiplication is negative 11 over 20 times vector A plus, and this portion will be 13 over 10 times vector B. Okay, so we're done. We just finished resolving the vector v into components parallel to vector a and b. What you can do is, if you could substitute the vector a and b into the final answer, you should get this back. That's how you would check the answer to make sure you did it correctly. Thank you.